Hello everyone and welcome. My name is Antonio Javier Nacalagel. I am tenure track researcher at Universitas Mercator in Rome, Italy, and webinar coordinator of the IEA Resilience Engineering Technical Committee. We are pleased to have with us to share this fourth and last presentation of a series of work on systematic method in complex and digitalized manufacturing, a webinar series organized by the Resilience Engineering Technical Committee of the International Economics Association. Today, Mr. Ali Caravan will share with us the collaborative work on the PSO-STPA meta model, case study of an Industry 4.0 plant using smart glasses. This presentation is based on an early journal paper published in Alien Journal and funded by the Natural Science and Engineering Research Council of Canada. Before we kick things off, I have a few housekeeping items to stay with us. We're expecting this webinar to last about 60 minutes. IEA is recording this webinar and it will be made freely available on the IEA website. We encourage you to send questions and comments through the presentations using the Q&A feature and use the chat feature for administrative issues. I will manage the Q&A, and we have time reserved at the end for answering your questions. And now, we'll give you a few details about our speaker. Ali Caravan is a PhD candidate in engineering at École Technologie Supérieure ETC in Montreal, specializing in risk management for a hybrid and complex manufacturing system with Industry 5.0 frameworks. With a solid background in the industry, we previously worked as industrial engineering manager and planning consultant in different manufacturing plants, bringing his practical expertise to academic research. His current research focuses on assessing the integration of smart wearables into manufacturing process to enhance safety and efficiency. He employs methodologies like STPA, Systems-Theoretic Process Analysis, and PSO, particle swarm optimization in his research, which aim to identify, assess, and mitigate risk factors in manufacturing systems. His publications have been published in journals such as Alien and International Journal of Quality and Reliability Management, contributing to a deeper understanding of human AA collaboration in industrial environments. Welcome, Ali, and I will leave you to take from here.
Thank you, Antonio. Hello, everyone, and thank you for joining this webinar. Today, I want to talk about the STPA-PSO model, a case study of an Industry 4.0 plant using smart glasses. This presentation is based on our published paper entitled A Comprehensive STPA-PSO Framework for Quantifying Smart Glasses Risk in Manufacturing. And if you're interested in reading the whole paper, I give you a few seconds to scan this QR code. Okay, so let's start by manufacturing advancement. Globally, almost every country's economies relies on manufacturing, and we've seen 5 major industrial revolutions so far. In 1784, the first industrial revolution took place. In that period, the number of workshops and factories increased. And after about a century, in 1870, the second industrial revolution flourished as mass production and assembly line aided in speeding up production. A century later, computers were developed, not only accelerating production lines, but also improving accuracy. Humans have been the main factors in industries until that time. And it's interesting to note that 50 to 90% of all industrial incidents resulted from human error. So Industry 4 was introduced in the last decade to improve industries and reduce human error by using new manufacturing systems and new manufacturing methods. In modern manufacturing systems, fewer human intervention are required as a result of use of new technologies such as robots, simulation, system integration, Internet of Things, cybersecurity, cloud computing, additive manufacturing, augmented reality, big data, and so on. A major motivation of use of these new technologies is their ability to reduce time and cost. However, Industry 4 has some negative points. There's not enough emphasis on the human performance, despite the German definition, which places human at the center. Systems in Industry 4 are complex, and ignoring the human element could negatively affect their performance. It may also contribute to social problems, such as increase in unemployment rate. Moreover, many modern equipment are extremely expensive from an economic point of view. And all of these issues contributed to the introduction of Industry 5 less than a decade after Industry 4 was introduced. We need not only intelligent machines, but also humans who can use these underlying technologies. System in Industry 5 should be human-centric to put human needs and interests at the heart of the production process, to be sustainable, to respect planetary boundaries, and to be resilient, to develop a higher degree of robustness. In Industry 5, robots manage repetitive tasks, which allowing humans to concentrate on creative and critical thinking, which improve production quality, and as a result, the risk of human error could be reduced. And unlike Industry 4, Industry 5 is value-driven, not technology-driven. Wearables like smart glasses, smart gloves, smart watches as part of this digital revolution. And many sectors can benefit from wearables, including healthcare, fashion, military, industries, and others. In manufacturing, smart wearables could help workers in maintenance, servicing, training, occupational safety, ergonomics, picking, and lots of other activities. Here you can see smart glasses and smart glove used at the Applied Human Factors Lab at École de Technologie Supérieure. It's important to note that while this technology can reduce human error, they also contribute to new challenges and risks, such as inability of workers to effectively use them, which we will discuss them later. And here you can see some components of smart glasses, which can be different based on their model, but mostly they have a camera for capturing videos and images, a battery, a GPS, a microphone for giving voice comments and instructions, connectivity, optic lenses, controls, and memory units. Now let's move to the term complexity and complex systems. In the last decade, there has been an increase in the use of term complexity. It refers to system structure as one aspect of complexity. It includes complex structures, complex networks, complex processes, complex information processing, and complex management. Also, there are two main types of systems, simple systems and complex systems. In simple system, one cause has one effect. A small change in a cause can result in a small change in the effect. And also, simple systems are predictable. On the other hand, complex systems are different. In complex systems, a small change in the cause can produce dramatic effects. And one cause can have multiple effects, and they are unpredictable. In socio-technical systems, social and technical elements are integrated into a defined objective. It's possible to consider socio-technical systems like the economy, manufacturing, healthcare, and education. The case study that we use is a psychotechnical system. Psychotechnical systems are formally considered as a complex system. Risk is a possibility of a negative outcome from an expected or desired outcome. There are different types of risk, and they vary in each industry. In this paper, we will concentrate on the OHS risk, financial risk, and the industrial risk. Financial risks include the activities that cause economic losses. OHS risks include events that affect human health, such as short-term and long-term health consequences. And in the case of industrial risk, there is the speed of the activity and generally technical activities that have led to production being stopped. And it's important to identify and assess potential risk to minimize all type of risk analysis. In order to estimate and effectively manage risk, various methods have been introduced. And you can see some of the main methods here, like functional resonance analysis method, or FRAM, from the Resilience Engineering School of Thought, System-Theoretic Accident Model and Processes, or STAMP, from System Theory, FMEA and FDA from Safety Engineering, Technique for Human Rate Prediction, Human Error Assessment and Reduction Technique, Systemic Human Error Reduction and Prediction Approach, Standard Plan Analysis, Risk Human Reliability Analysis from Reliability Engineering, Cognitive Reliability and Error Analysis Method, and a Technique for Human Error Analysis from Cognitive Engineering, and Bayesian Network from Artificial Intelligence. These techniques are divided into qualitative and quantitative. However, to effectively manage the risk of Industry 4 applications, systemic methods should be used. STAMP-STPA, FRAM, IST, AXIMAP, and CWA are among the systemic methods. Based on the concept of system theory, STAMP was developed in 2004 by Nancy Leveson to deal with complex systems. This approach addresses the limitation of traditional accident analysis method. STAMP identifies root causes of accident more comprehensively than other system theory methods. In the context of hazard analysis, STAMP is known as STPA, while in accident and incident analysis, it is known as CAST. STPA is among the most widely used proactive analysis method based on STAMP. STPA assumes that system component may have failed, but the accident can still occur due to unsafe interaction within them. STPA is an effective method for identifying safety requirements and constraints in early concept analysis. And a major benefit of STPA is the ability to trace decision and design throughout the development process, which we use in this study. The particle storm optimization method, or PSO, was introduced in 1995 by Kennedy and Eberhard. They modeled this algorithm by taking inspiration from observing the behavior of animals during accretion and aggregation. It's one of the well-known swarm-based optimization methods. Instead of producing new samples, PSO saves significant statistical population. The members of that population are optimized based on discoveries. And as the PSO relies on heuristic approach, it doesn't guarantee the optimal result. As you know, PSO has proven to be a highly flexible and practical tool for solving complex optimization problems. It's widely adopted in various optimization domains due to its ease of implementation and effectiveness. Several control parameters influence the basic PSO, such as swarm size, acceleration coefficient, the weight of inertia, the neighborhood size, and the number of iterations. It starts by initializing a population of particles with random position and velocities in a defined search space. Then we need to evaluate the fitness or objective function of each particle. Then we need to compare the fitness evaluation of each particle with the current particle to determine the personal best. Then we need to compare the fitness evaluation of each particle with the population previously best to determine the global best. Then we need to update and adjust the velocities and position of particles based on their past behavior. And at the end, we need to check if the determination criteria are met, for example, the maximum number of iterations. And if not, we need to repeat the mentioned steps until a stoppage criteria satisfied. By analyzing the literature, we found only 3 papers which concentrate on assessing the risk of using wearables to the complex system. However, all of them are qualitative, and there was a gap in quantifying the risk of using wearables in complex systems. And now I want to mention the main objective of this paper. As you can see, we have two main objectives for this paper. The first one is introducing smart glasses into a complex system. And the second one is to develop the STPA-PSO methodology for identifying, analyzing, and quantifying the related risks. Now let's discuss the STPA-PSO method that we use in this study. First, we need to determine the case study. Then we need to determine the purpose of study, then identify losses, hazard, and system-level constraint. To better understand the concept of these terms, I read their main definition given by Levison. A loss involves something of value to stakeholders. Losses may include loss of human life or human injury, property damage, environmental pollution, loss of mission, loss of reputation, loss or leak of sensitive information, or any other loss that is unacceptable to the stakeholders. A hazard is a system, state, or set of conditions that together with a set of worst-case environmental conditions will lead to loss. A system-level constraint specifies system conditions or behaviors that need to be satisfied to prevent hazards. In the second step, we have to model the control structure. Control structure typically encompasses 5 essential components: controllers, control actions, feedback, inputs and output from components, and processes controlled by the controllers. In the next step, we need to identify unsafe control actions. What is unsafe control action? It is a control action that in a worst-case environment will lead to a hazard. In the fourth step, we need to calculate the risk of each event by their probability and their impact. We need to assess the impact of each event, and we have considered 3 aspects in this study, including industrial, financial, and OHS aspect. Then by using best worst method, or BWM, we assess the impact of each aspect. For the probability, we use Monte Carlo simulation. Then by using MATLAB, we calculate the model, and at the end, we select top events with the highest risk factors for analyzing the loss scenarios. To calculate the risk of each event, we need the probability of that event, or PI. We need the weight and impact of industrial aspect, the weight and impact of OHS aspect, and the weight and impact of financial aspects. As I said, the weight of each aspect is determined by the BWM method. And the impact of each aspect is based on 5-point scaling from very low to very high. The scenarios that we use for industrial and financial aspects are demonstrated in the first table. As you can see, we have no economic or industrial loss, delay in production like breakage of some parts, materials, equipment, or no receiving materials. We have reassembly, we have major damage to the product or equipment, and stop production. And for the OHS aspect, as you can see in the second table, we consider that an event can have no impact or no effect on OHS aspects. It can have an injury that requires first aid only, resulting in short-term pain, irritation, or dizziness. It can indicate conditions like sprain, strain, burns, skin condition, and injuries requiring time off from work. Or it can denote severe conditions such as broken bones. Or for very high impact, it represents critical situation involving excessive bleeding. Now let's talk about our case study. Our case study focuses on a refrigerator manufacturing plant in a design phase. The refrigerator moves alongside an assembly line or a conveyor, and the required assembly tasks are completed at each section. Assembler needs to assemble 3 parts, and we consider that each part is located in a bin near him or her. The assembler received the refrigerator from the previous section, assembled the required part based on the refrigerator model, and then send the refrigerator to the next station. To establish a reliable STPA, we need to define the whole process carefully, and I will read the process now. First, sales order and market demand are checked by the production planning unit. Next, the production plan is developed based on the parameters available. Then a detailed production plan is sent to all units involved, like production, quality control, warehouse, sale, maintenance, etc. The warehouse department provides the necessary material and parts according to the production plan. Production personnel receive workshop planning from the supervisor with product map, technical specification, and require instruction for each station. Assembly is performed according to the supervisor's order and the production schedule and requirement. According to the type of product, it may be necessary to assemble a certain number of each part in the refrigerator, which is specified in the product map. Assembler must correctly place the required parts in the correct places with the help of smart glasses. Consequently, the worker must take each part from different bins next to him with the help of smart glasses. And in addition, the warehouse department is responsible for completing these parts to prevent interruption at the assembly line. Finally, the product is sent to the next workstation. Now let's discuss the result of applying STPA-PSO to the case study. In the first step, we found 4 losses: injury to the worker, unacceptable damage to the product, unacceptable damage to the component and equipment, and financial loss resulting from delayed operation. Then we identify associated hazards, including harmful activities such as ergonomic issues, limited field of view, distraction, and fatigue, which may lead to injuries among workers. The second one related to insufficient training of workers, which posing potential risk. The third one occurs when materials are not received on time, potentially causing delays. The fourth one related to the absence of timely feedback, potentially leading to operational inefficiencies. And the last one concerns the transmission or reception of wrong data, which could lead to various issues. The next step is to determine the system-level constraint based on the identified hazards. Each system-level constraint can be related to multiple hazards. Here we have, for example, supervisor must check workers' work periodically to ensure they know how to do their task. We need to consider sensor positioning and glass speed based on the worker during design phase. We need to calibrate the data glass based on the manufacturing instructions. We need to ensure effective and reliable communication channels between the supervisor and the production planning department to ensure reliability of the data. The IT department must apply proper instruction to ensure the proper and reliable feedback of the data glass. And the connection between receiver and processor and the smart glass should be checked. Here you can see the control structure of this model. This graph shows the interaction between each department. It shows how departments can communicate and get feedback from the other department. You can see, for example, here, the smart glass received data of positioning of the product and material from the assembler and give him the light command, which determine the position of the assembly and the material to be used. The other example, smart glasses received the production map and assembly instruction from the production department and give them the assembly report, worker performance report, instant display, and real-time communications. Then unsafe control actions, or UCA, should be identified. These are actions that under certain conditions could lead to hazard. For example, here we have the training department provide insufficient training for workers, or smart glass is not calibrated before use. or the IT department doesn't provide programming for the receiver and processor, or the smart glasses do not provide feedback about the place of assembly to the worker. The receiver and processor do not provide light comments. The next one is the smart glass provide drawing feedback to the worker. And the other one, the receiver and processor provide drawing light commands. Then by using the STPA-PSO model, we can quantify the risk level associated with each unsafe control actions. Based on the risk matrix table, high and very high risk factors events were identified and selected for loss scenarios analysis. Now the question is, are there other improvements for this model? The answer is yes. We have introduced two extensions so far. The first one was presented in the last year's IEA conference at South Korea, and we defined a framework to integrate a machine learning algorithm to this model, which dynamically updates the results. And the second one is currently under review, but you can find it through SSRN. We propose a circular methodology which helping decision makers by providing mitigation strategies for the identify risk and then recalculate the whole model. To conclude the presentation, we integrated STPA with PSO to quantify risk, including human error risk. We demonstrated the practical utility of the methodology through a case study on a refrigerator assembly. This methodology successfully identify, analyze, assess, and quantify the risk of using smart glasses in the case study. This paper offers comprehensive analysis encompassing industrial, financial, and OHS aspects. And in my opinion, the weak point of the STPA method is the fact that it's complex for individual to apply it, and it can have different results based on how you define the system. And finally, I want to mention that simulated data used in this paper. Thank you for your attention, and I'm ready if you have any questions. Thank you.
Thank you, Ali. Some question for the audience? Yeah, we have a question, Ali. Now, what does the algorithm need to use to inputs to create unsafe control action in the mentioned framework?
Please wait.
It's in the webinar chat.
What does the algorithm need to input to create unsafe control actions in the mention? Okay, for the input for control actions, we need to first define the control structure model. Then based on the unsafe control actions, we define, based on the PSO algorithm, we defined probability and the impact for each aspect. We given to the algorithm, and then we receive the risk of each unsafe control actions. I can't hear you, Antonio.
Sorry, now we have another question, okay, for the audience, in which we thank you for your great presentation. Can you please give me the link of the paper in SSRN, please?
Yes, for sure. Just send me an email. I will send you the link of the paper.
Thank you. Now I will introduce our webinar chair, okay, organizer chair, Sylvie Nadeau. Okay, please, Sylvie, take the lead.
Thank you, Antonio. So very sorry I was late this morning. So my understanding is that the questions are finished. The questions period is finished. Okay. So look, thank you, Ali. Thank you, Antonio. Thank you to IEA. Thank you, everyone, for joining this webinar series. Please note that attendees will receive a web link for a past webinar survey and an attendance certificate will be delivered if you respond to the questions correctly. The TC chair, Professor Patriarca, would like to inform the resilience engineering community of 2 upcoming opportunities. One is a call for abstract for the 17th International Family and the 7th International Workshop on Safety 2 in Practice, the 12th to the 16th of May, 2025 in Delft in the Netherlands. The deadline for the submissions is March 20th, 2025. So maybe, Ali, if you could share the slide where you have the QR codes for those 2 conferences. And
Yes, sure.
thank you very much. So the other call for papers is for the 11th Biennial Resilience Engineering Association Symposium and the 14th Annual Resilience Healthcare Society meeting that will be held between the 20th and the 24th of October 2025 in Canela, Brazil. And the deadline for the submissions is March 31st, 2025. So this is the end of our webinar, our 4 webinar series. I do hope you really appreciated this series, and well, keep informed, keep yourselves informed, because this is a very dynamic technical committee, and there will be those 2 activities coming up, but other activities planned by the chair committee in different soon. Thank you very much. So thank you very much. Have all a nice weekend. Bye-bye.